Hello everyone, so today we're going to go over section 10.1, understanding logarithms. So the logarithm of a number is an exponent. It is usually written in the form of log base c of x. Suppose we have an expression in exponential form. And that is x is equal to c to the y power. A numerical example could be that 25 is equal to 5 squared. So the x is the 25, the base c is 5, and the y, which is the exponent, is 2. The logarithmic form of the same expression looks like this. And that is y is equal to log base c of x. So that is 2 is equal to log base 5 of 25. In other words, a logarithm is really asking the question, if 25 is to be written as a power of base 5, what would the exponent be? So it will be 2. Of course, the logarithm has an associated function, and we have y equals to log base c of x. So the y here is the value, that is to say the exponent. C is the base. And x is the argument, which is usually a power. So just as with exponential function, our base has to be greater than 0 and not 1. Okay. And recall that the values of an exponential function are always positive, so here the arguments will be positive always. The value, however, which is the exponent, could be positive or negative. So one of the first things we want to be able to do is to rewrite logarithmic forms into exponential forms and vice versa. So here we have log base 7 of x is equal to 4. In exponential form, this would have the base of 7 raised to the 4th power, the exponent, and that will be equal to the argument, and that is the power x. Similarly then, on the right-hand side, we will have 5, the base, to the y power, the exponent, and that will be equal to the argument of 15. Here, very similarly, we are going to rewrite this one as well. The base is the variable t. The power is m. Sorry, the exponent is m. And the value is b. And finally, this last one, we will have b to the 5th power is equal to 6 to the 4th power. Okay. in example 2, we will convert from exponential form to logarithmic form. Starting with the first example once again. So here we have 4 to the third power is 64. So as a logarithm, this will be log base 4 of 64 will give us the exponent of 3. Example B, the base here is 2. The argument is the power of 1 over 8. And on the other side, we have the exponent, which in this case is negative 3. Next couple, log base e to the of f is equal to d. And finally, we have log base a, and then the argument is the power, so 2x plus 4, and that is equal to 5. So here, we are going to introduce the common logarithm, which is just logarithms with base 10. So if the base is not written out explicitly, so for example here, then we always assume that the base is just 10. So in other words, log 3 is equal to log base 10 of 3. Now that we have an idea on how to convert between exponential and logarithmic form, we will use that to evaluate logarithms, starting with number 1, example 3a. So we have log 0.001. Given what we know from before, we know that this is log base 10, and we can also rewrite 0.001 as a fraction, and that will give us 1 over 1,000. So in other words, we're asking 10 to the power of what number is equal to 1 over 1,000. So we know that first of all, it should be negative, and then because of the fact that it's 1 over 1,000, and 10 to the third power is 1,000, so altogether then we have negative 3. Okay. So another way to work with this logarithm questions is to set it to be equal to x. So now we can rewrite the entire thing in exponential form. We have 4 to the x is equal to 1 over 64 on the right-hand side. So now then, of course, we can rewrite the right-hand side as 4 to the negative 3 power. And in conclusion, we have x is equal to negative 3. Okay. Let's look at the next example. Again, we can set it equal to x. So here, 6 to the x power is equal to 1. And therefore, x must be equal to 0. And finally, on the last example here, again, we set it equal to x on the right-hand side. So now we have 2 to the x is equal to the square root of 8. Okay, so if we were to rewrite the square root of 8 as a power of 2, we'll have 2 cubed to give us 8, and then to the 1/2 power to give us the square root. So combined together, we know that x is equal to 3 over 2. So again, the argument should be positive, and the base should also be positive, but not 1, just to reiterate what we saw on the last page. Okay. So in the logarithm questions, there are 3 different unknowns that could be that we could solve for. There is the argument, there's the base, and there's also the value bit that is just evaluating, which we already did. So example 4 will focus on looking for the argument and the base. So get the first example then. We have 5 to the negative 3 power is equal to x if we were to rewrite the expression in exponential form. So x is simply equal to 1 over 125. Okay. Next, we have, again, rewriting in exponential form gives us x squared is equal to 36. So x could have been either 6 or negative 6. However, we need to reject negative 6 because x is a base and it needs to be greater than 0. One more. So here we have x is equal to 64 to the 2/3 power. So in other words, x is equal to the cube root of 64 squared, like so. So of course, the cube root of 64 is 4, and 4 squared gives us 16. Now, so far in our examples, the argument tend to be powers of the base. So for example, we will have something like log base 2 of 4, and of course 4 is a power of 2. If we look at example number 5, we can see that we have log base 2 of 14, and 14 is not a power of 2. So in such cases, we need to estimate its value. And the way that we're going to do that is simply take log 14, so using the common logarithm, and divide that by log 2. This is an application of what's known as the change of base rule. And the details of this will be covered in a later section of this unit. But for now, if we're just going to be using a calculator, we can plug in log 14 divided by log 2, and that will give us an approximate value of 3.807, etc., etc. Which makes sense because 14 is very close to 16, and 2 to the 4th power is 16, so it should be less than 4. Now, the reason why logarithms are useful is because a few of the scale that we used in real life are actually logarithmic scales, or where the increase in magnitude is exponential. So earthquake magnitude is one of them, pH value is another, and finally the loudness of sounds is another example of this. So let us consider the following examples. Example 6. So there are 2 earthquakes, one of which has magnitude 8.5, and then another has magnitude of 6.9. If we are to compare the intensity of each, then the actual intensity of the first is 10 to the 8.5 power, and the second will be 10 to the 6.9 power. Now, if we are to compare these two, as in how many times more intense is the first earthquake compared to the second one, we will divide these two magnitudes, written as powers of 10. Now we're dividing powers of the same base, which means we're going to subtract the exponents, like so. And so this will be 10 to the 1.6 power, which is approximately 39.8 times as intense. Example 7. So very similar. An earthquake in San Francisco had an amplitude that's 1,000 times larger than the earthquake measure 4.9 on the Richter scale. What would the San Francisco earthquake measure in terms of its intensity once again? So in this case, we know that let x be the value on the Richter scale. If we subtract 4.9, we will get the 1,000 times, which is 10 to the third power. These are both powers of the same base, so we have x minus 4.9 is equal to 3. So x is going to be equal to 7.9, and that is what the San Francisco earthquake would measure, 7.9 on the Richter scale. One more. Example number 8. The loudness level of a heavy snore is 69 decibels. The loudness level of the conversation is 60 decibels. How many times as loud is one to the other? So the difference is 9 decibels. So that will be 10 to the 9 over 10 is a decibel, so it's 1/10 of the difference. So 10 to the 0.9 power then. And that will give us an approximate value of 7.9 times as loud. And that's it. So we've looked at the definition of logarithms today, how to convert from exponential to logarithmic forms, and using that information to solve a few simple equations and look at some applications of logarithms. And that's it for today, so thank you for listening.